All right, so we finally made it. We finally made it to the fundamental theorem of calculus. And it's going to be split into two parts, so it's going to have a part 1 and a part 2. And I guess this is our last lecture video. At the end of this, once I've finished recording this, what I'm going to do is I'm going to film a video recording the proof of the fundamental theorem of calculus, but because I want you to focus on how to use it, I'm not going to include that in this video. Instead, I'll just add kind of an extra video to that if you're interested in the proof of it. It's very, very neat, but you don't need to know the proof in order to use it. You just need to know kind of how to understand it. And in conjunction with the fundamental theorem of calculus, we're going to be talking about the indefinite integral. So this is kind of mixing both 5.3 and 5.4 together. Okay, so our first situation we're going to be dealing with is f is going to be a continuous function over some closed interval, a to b. And if you've watched some of the other videos leading up to this one, this is kind of a familiar situation we're working with. So we draw a picture, here's our continuous function, and here's our interval that it's defined over, a to b. Well, one thing you can do is you're given this function f, so this is going to be the curve y equals f of x. And actually, instead of x, what I'm going to do is I'm going to call this variable t. So this is going to be the t-axis. This can still be the y-axis. That's fine. Because what I want to do is I want to use the x variable to be a choice between a and b. So I'm going to pick some x value there. Any x value between a and b. And what I'm going to do is I'm going to say, well, given this x value, what I would like is I would like you to tell me what this area is. So I pick some value between a and b, and I want to compute that area. Well, we know what that is. We know that if I look at the area here, this is going to be equal to the integral from a to x, because we're stopping here at x, of ft with respect to t. Remember, we have the t-axis, so that's going to be fine. And why I chose x is because notice that if I choose a different x value, like x0, well, that's going to give me a different output if I change that thing there. It's going to add a little bit of area to it. So you're just going to kind of add that area there, and it's going to give you a different number as the output. So I can actually think of this thing as another function. This time it's a function of x. I'm not thinking of it as taking in the variable t. I'm thinking of x as being a variable that changes between a and b. Now, this kind of allows us to have functions and create new functions. So we've seen that before when you're talking about derivatives. You have functions and you take derivatives and you get new functions. So this is, again, kind of another way that's similar in that sense that you have functions and you get new functions from them. Now, it's not taking the derivative. It's very different from that, and we're going to explain the relationship in a second. But the idea is it gives you a new function. Now, what happens if, say I have the same function here, and here is, again, a, and here is b, and maybe over here we have d, and I want to now think of the function g of x that starts at d and picks some x value between the interval d to b. So some x value there, and inside you have f with respect to the t-axis there. Well, what's the difference between g and f? Well, here's the idea, is it's really only going to differ by this kind of starting chunk here. And this is just an area. It's just a number with a specific value. So we can call this area, call it some constant c, it's just some constant value. Well, notice that g of x is going to be equal to d up to x of f of t dt. And I can break that up into d to the a, f of t dt, plus a to x, f of t dt. And this thing here is just going to be equal to the area of this strip, which is just c. So remember, you can break up integrals like that. And that's from the properties of integrals. And so maybe I should write that down. This is properties of ints. And this is just going to be c plus, well, this thing here, dt. But this is just f, your big F function, f of x, and then we have plus c. And so the punchline is that this g of x is actually just equal to big F of x plus c. So the idea is, if I have a function that, is defined on all real numbers, yeah, I can define it on just closed intervals. Or maybe it's not even defined on all real numbers, but I want to look at specific intervals. And I want to start this new function at different values. Well, they're actually going to be the same function, they're just going to differ by a constant. So not exactly the same function, but they'll differ by a constant, and that's it. Okay, so now we're going to be looking at a motivating example, and this is going to help motivate the fundamental theorem of calculus. And so the idea is, suppose a particle travels at a constant velocity, that's going to be k, and we can think of it in meters per second. Choose your favorite units, it could be feet per minute, it doesn't matter. As long as you kind of understand what the time variable means. Then can we tell how far it's traveled after t equals x number of seconds? And the answer is going to be yes. We can, because if it's traveling at a constant velocity, and we know it's gone x amount of seconds, then this is going to be the distance that it's traveled, right? Well, that makes sense. Another way to think about this is, suppose we have a picture where we graph the velocity function. So here we have our function. It's going to be with respect to t. So t is going to be our x-axis. And this will be our y-axis, and we want to graph f of t with respect to y. Well, if f of t is just always equal to k at any time, the particle's velocity is always constant, well then what you're going to get is, well, we're probably moving at a positive rate. This is just going to be value k, and the graph is going to look like that. Okay? Well, now what I'm asking is, I'm asking after x amount of time, how far have you traveled? Well, after x amount of time, we know we've traveled k times x. Well, what's another way to visualize k times x on this thing? Well, if this is 0 and we're tracking it from time 0, if we look at this rectangle, then what we're going to have is we're going to have x, and then all the way up to k. And so we can think of the distance traveled as equal to the area of this rectangle and that thing, I'm just going to call that big F of x this time, and I'm going to write that as 0 to my x value of f of t dt. And what do we know? We know that if we have just a constant in an integral, that this is actually just going to be equal to, it's going to be equal to k times b minus a. But in this case, b minus a is just x minus 0. And so again, we get k times x. So we can compute this integral too. This is again just using those properties of integrals. So properties of ints. But we also knew from our picture that, yeah, this is just going to be equal to x times k. In other words, notice that if we take the derivative of our big F, which is x times k, what do you get? You just get k. And this is just equal to f of x. It's equal to our function f. So notice that f, big F, is an antiderivative for little f. And big F is this integral function that we just talked about in the previous section. So this is kind of neat. We've found antiderivatives in terms of these integral functions. And this actually isn't special. This is what the heart of the fundamental theorem of calculus is all about. All right, so here is the fundamental theorem of calculus part 1. And sometimes we call this FTC and then like part 1. So we shorthand it to FTC. Okay, so the setup for the fundamental theorem of calculus is you just need a continuous function. So actually let me write it in the third panel. So here you have your continuous function. This is f, and it's going to be over some closed interval, a to b. And what we're going to do is, I'm actually going to call this axis the t-axis, because what I'm going to do is then this function here, f of x, I'm going to create it from a to x of f of t dt. Now, one thing I want to keep in mind is it doesn't matter if I think of my variable inside f of x, little f of x, as x or t. Sometimes this is called a dummy variable. And it is just kind of a change of name. It doesn't really matter. But it's going to help us keep in mind what is the variable that's actually changing here in this function. It's going to be the choice of x that you're making in this interval. That's going to be the thing that's changing. So the t is just kind of a dummy variable. It's what you're taking this integral with respect to. So what are we going to do with this? If f of x is a continuous function on the interval a to b, then this function here, what's special about it? Well, it's going to be continuous, is continuous on the closed interval a to b. That kind of makes sense if you kind of shift it a little bit. It's going to move a little bit. You can kind of control how the area grows as you change your x value. Also, and differentiable on the open interval from a to b. Remember, in order for something to be differentiable, we want it to be defined immediately to the right and immediately to the left, so we don't really include the endpoints there. But this is something that's special that's happening, is you have a continuous function and you can create a differentiable function from that in this way. So that's kind of neat that you get something that's like more powerful than your original function. Well, not only is it differentiable, but and if you take the derivative of big F, what do you think you get? Well, in the previous example, that motivating example, we got the function that was inside the integral. And that's exactly what happens. You get the function that's inside the integral. And so this is so very, very special, and we're going to harp on it more and more, but what it's doing and what you should kind of take away from this is it is connecting the integral that we just talked about as this problem of area, and we developed it based on that. It's connecting it to antiderivatives. So the big idea of derivatives now kind of has an opposite idea in terms of an actual problem, a problem of area. And it's kind of in this special way. So I'll come back with the second part of the fundamental theorem of calculus. And that's actually going to be probably the more important one, because it's going to help us solve this problem of area. We actually don't have that solution yet, but the second part of the fundamental theorem of calculus is going to close that gap. All right, here is the fundamental theorem of calculus part 2. Brain fart. All right, so here is the fundamental theorem of calculus part 2. If f of x is a continuous function, again, our setup is f of x is a continuous function from the interval or on the interval a to b. And so this is f, and we have big F of x, and this is any antiderivative of little f of x. So you choose your favorite one, whatever you want. Then what you're going to get is, if I want to compute this area here, well, that's going to be the integral of f of x with respect to x from a to b, and this is just going to be equal to big F of b minus big F of a. And sometimes this is just written as large F of x, and you put this bar here from a to b. And this just means the same thing as we need to evaluate f at b and f at a and take their difference in that way. Okay, what is amazing about this is, again, yes, the integral, this actually says more than just the area problem. It tells you what the integral solution is, and we know that integrals aren't necessarily areas under the curve. Sometimes the function dips below the x-axis and they become signed areas under the curve. But if we have a situation like this, where f is always above the x-axis, we can interpret the area under the curve as this integral. And if I want to compute that area, all I have to do is know an antiderivative of f and evaluate it at the limits, take their difference in this way, where b is always going to be the one you take first here, and then you subtract f of a. Okay, so let's look at an example. So this is going to be example 1. I know we saw another example, but that was a motivating example. So this will be example 1, and the idea is we want to compute the area under the curve y equals sine x over the interval 0 to pi. Okay, so compute. Okay, so here's the solution for this. And we're going to use the fundamental theorem of calculus. So what we do is we first draw our picture and we look at sine. It's going to look like this. And we notice that from 0 to pi, this thing is always going to be non-negative. So it's always going to be above the x-axis. So sine of x is always greater than or equal to 0 when x is between 0 and pi. That's great. So what we can do is we can look at the area of this thing here. Notice that sine kind of keeps going and does its own wavy thing, but we're just worried about this. We can look at this and we can interpret that area as equal to this integral from 0 to pi of sine x dx. So we've written it as an integral, but we want to get it as a number. Remember, whenever you have a continuous function here and you have your limits written there and their actual numbers, this always stands for a number. Okay, so how do we evaluate it? Well, we're going to write it as big F of x from 0 to pi, where this big F of x is an antiderivative for sine x. And I get to choose any antiderivative I want. But what's one that we know about? Well, we know that if you take the derivative of cosine of x, you're gonna get negative sine of x. So if I take the derivative of negative cosine of x, I get sine x. So what that means is negative cosine of x is an antiderivative for sine of x. So I'm going to rewrite this as negative cosine x, evaluate that from 0 to pi, and this means I'm going to do negative cosine of pi minus negative cosine of 0. And now I have to remember my cosine values. Well, cosine of pi is negative 1. Cosine of 0 is 1. So what I'm going to get is negative 1, minus negative 1. So that's going to give me 2. Okay, so now let's think about this answer. Oh, yeah. Sorry, I wasn't sure if it was showing up or if it was cutting off. That's why I looked close into the camera. I apologize, that must have been frightening. Let's make sure that this answer makes sense. We're talking about an area. Well, it's not a negative number, so that's good. And I can see that this actually has area to it, so it can't be 0. So these are things to make sure that you've worked your thing out correctly. Now, these are just quick checks, but it's things you should think of when you're working through integrals. Is it always positive? If the function is always positive or always above the x-axis, I should always get a positive number. And this can actually really be helpful when you're working with trig functions. If it's always below the x-axis, you should always be getting a negative number too, because you should be thinking of that as negative area. So these are just real quick checks to make sure you've done it correctly. Okay, so that was example 1. We're going to see example 2 in a second. Okay, so here we are given kind of this crazy function here, 3x to the 4th minus the square root of x plus 2 over x from 1 to 2. And the first thing we want to do is we want to make sure that this is actually a continuous function over this interval, because if it isn't, then it doesn't really make sense. Well, we know the interval from 1 to 2, it's always going to be positive numbers. I can always plug in all of those numbers into x to the 4th. I can plug them into the square root of x, and I can divide by all of those numbers, all the numbers between 0 and 2. So I'm good. There's nothing wrong with that. If there was a discontinuity, if there was something amiss and something that wasn't defined over that interval, there are ways to handle that, but you have to be careful. Anyway, so we can use the fundamental theorem of calculus on this. But before we do that, we're going to use the properties of integrals to simplify this. And what I mean by simplifying it is I'm going to distribute the integral to each piece over all of the sums. So I'm going to rewrite this as 3 times the integral of 1 to 2 x to the 4th dx. So one thing you should notice is I distributed it onto this piece and I pulled out that 3. Remember, I can do that. I can pull constants out. That's properties of integrals. So I should say properties of integrals. And you should look these up and make sure I'm doing them correctly. And then it's going to be minus the integral, again, from 1 to 2, of the square root of x. But what I'm going to do is I'm going to rewrite that square root of x into x to the 1/2 dx. And then I'm going to get plus the integral from 1 to 2 of, well, I have a 2 over x, and I can rewrite that as, I can pull out the 2 and rewrite the x as to the -1 dx. Why did I do that? Well, one of the reasons I did that was because I have a rule for how to work with each of these. Notice it's just x raised to a power. So I know antiderivatives for x raised to a power. I have the reverse power rule. Or if you want, the power rule for antiderivatives. If you have x to the n and you want an antiderivative for this, that's going to be, well, so if you have a function here and we have antiderivative, so here we have x to the n. Well, as long as n is not equal to -1, what you get is this is x to the n plus 1 divided by n plus 1. So remember, if we take this derivative, we get that. Now, what is the case? The one case left is when x is raised to the -1. Well, in this case, what you have is you have natural log of absolute value of x. Because remember, the derivative of natural log of absolute value, x, is equal to 1 over x. All right, so all of these things are going to be important because they cover all of our cases. So this is just going to be 3 times an antiderivative for this evaluated from 1 to 2. Well, this is x to the 4th, so I'm going to have x to the 5th divided by 5. This is going to be minus x raised to the, what's 1/2 plus 1? 3/2. And if you divide by 3/2, that's the same thing as multiplying this by 2/3. And you evaluate that from 1 to 2. And then this is going to be 2 times, well, this is x to the -1. So you're going to get natural log absolute value of x from 1 to 2. And it's important that you remember the absolute value of x because you can define a function like this for negative values. But remember, you can only plug in positive values into the natural log, so you need that absolute value. Even though it's not going to affect us now, we're only working with positive values. It's important that when you're working through this thing, you do natural log of absolute value of x. All right, now I just have to evaluate these things. And this is where it can kind of take a little bit of time. So this is just going to be 3 times 2 raised to the 5th, 32, over 5, minus 1/5, minus, well, if I plug in 2 and raise it to the 3/2, that's going to be square root of 2 to the 3, or square root of 8, which is just 2√2. And so if I plug in 2 there, I'm going to have 2 times 2√2, or 4√2 over 3, minus, plug in 1, you get 2 times 1 over 3, 2/3. And then this one is going to be plus 2 times natural log of 2. Notice I dropped the absolute value. That's because absolute value of 2, 2. Minus natural log of absolute value of 1, natural log of 1. Well, what's natural log of 1? That's just 0. So that simplifies that. And now I want to combine these things. So this is going to be 31. And I'm going to have 31 over 5 times 3, or 93 fifths. And then I'm going to have minus 4√2 over 3 plus 2/3 plus 2 natural log of 2. And you could probably leave it like that. That's fine. If you're working through something like this on the exam, you can leave it like this, but you can also combine 2/3 and 93 fifths by multiplying this by 3/3 and multiplying this by 5/5. If I multiply this by 3, I'm going to get 279 over 15, and then I'm going to add 10 over 15, and then I have minus this 4√2 over 3 plus 2 natural log 2. And what I'm going to get is 289 over 15 minus 4√2 over 3 plus 2 natural log of 2. And that's going to be your answer. Now, for this problem, I was just asked to compute this integral. I wasn't asked to interpret it as an area, and actually I don't know if it's an area. I don't know if it dips below the x-axis at some point. Maybe it does. Maybe at the very beginning it dips below the x-axis, in which case it would be signed area. But I'm not actually sure. I could take the derivative of this function and see, is it increasing and does it start at always being above the x-axis? That's one possibility, and actually it does look like that. And it looks like it's going to be increasing on this interval, so I would assume that, that this would actually be an area. But I can't use my double check. That should be a plus there. So I just kind of have to hope that my calculations were right. And that's kind of how you work with these more complicated examples. All right, so now this is just essentially some notation, but it has a name, and it's a very, very important thing. So remember back in 4.9, we were talking about antiderivatives. We were talking about antiderivatives, and we would phrase it as find the antiderivative of this function, or find antiderivatives of this function. Well, now, in light of the fundamental theorem of calculus, we have a meaning for antiderivatives, and they show up when you're evaluating these integrals. So we would like to characterize them in terms of integrals. So a lot of times what we do is if we have a function f and we know an antiderivative, so this isn't unique. Remember, antiderivatives, there are usually a lot. There are an infinite number of antiderivatives of a function. If you have an antiderivative of f, what we're going to do is we're going to use this notation here, which we call the indefinite integral. And this is just going to mean f of x plus c, large f of x plus c. And this is called the indefinite integral. So a couple things to note is, notice it's called the indefinite integral because it doesn't have limits to it. It's indefinite. We don't put an actual value on it. Another thing to notice is, remember, all antiderivatives for a function just differ by a constant. This was a consequence of the mean value theorem. So if you want to go and prove that for yourself, go back and look at what we talked about in the mean value theorem. Specifically, there's a final corollary we talked about at the end. And it just tells you that if you want to look for antiderivatives of a function, all of them are just going to differ by a constant, and that's going to be it. And so what's going to happen here is we're going to use this notation to mean all of the antiderivatives of this. And that's what that c means there. So the c, actually, you can think of as a, pick your favorite constant, or a variable constant in a way. So it's a little weird to deal with at first, but that's what it means. It could be 2, it could be 3, it could be 5, it could be negative 12, 0, it could be pi, all of those things. And this is going to be what the indefinite integral is going to be. So just to kind of recap, we have these 3 different symbols that all use the integral notation. The first one we saw was something like this. And this was the definite integral. And this is always a number. So the definite integral is always a number, as long as it's well defined, as long as it means something. Because remember, it's the limit of something. So I guess it could be does not exist, or it could be infinity or negative infinity, but we usually don't define it in those cases. So this is going to be a number. If we write something like this, then we're thinking of this as is a function, and it's going to be a function of x. You want to keep in mind that that's the thing that's changing. The t is just a dummy variable. And if we don't have anything on these things, and we use this notation, this thing here is a family of functions. So remember, we talked about that idea of a family of functions. They all just differ by a c. So this stands for all of the antiderivatives. And this is kind of a sticky point, but these 3 things all mean different things. So whenever you see something like this is always just going to be a number. Whenever you see something like this is going to be a function. Whenever you see something like this isn't just one function, this is an infinite number of functions. It's a family of functions. But it's a convenient way to write what are all of the antiderivatives of this function inside here. Okay, so let's look at a question here. This is going to be example 3. what we have is we want to compute the integral. We have sine to the fourth x cosine x dx. And this is an indefinite integral. So what is this asking us to do? It's asking us to compute the family of antiderivatives of this function here. So you have this small f of x being sine raised to the fourth cosine x. And we want to find an antiderivative for that. And then if we can find one antiderivative for that, then all of them are just going to be that function plus a constant. All right, so this can be a little tricky because we don't have a rule for this. This isn't one of those basic things. So what you might recall, and this might get to the point that whenever you're going backwards, whenever you're finding antiderivatives for something, it's usually a lot harder than finding derivatives. And so I want to stress that. If you take Calc 2, you'll find out how to compute these things in maybe a more standard way. But for now, it's just kind of an ad hoc method. You kind of have to go through and you have to think, well, what function would I have to take the derivative of to get to this? So you might play around with this a little bit, and you might remember that if I have sine raised to the n of x, and I take the derivative of that with respect to x, well, remember this is just the derivative of sine x raised to the n. So I can use the power rule and get n times sine of x raised to the n minus 1, but I also have to use the chain rule. And then what I'm going to get is I'm going to get n times sine raised to the n minus 1 x times, what's the derivative of sine? Cosine x. So in a sense, this actually kind of looks like that, except here, you know, if we replace this with 5 sine raised to the 4 x cosine x, kind of looks like that, except you have this extra 5. Well, how do we deal with that? We bring this down, and I think of it like this, where I multiply by 5 over 5. All I'm doing is multiplying by the number 1, so nothing changes. Now I'm going to leave a 1 over 5 on the outside, and I'm going to bring a 5 inside. And now what I have is this thing is equal to this thing, is equal to this thing, and this is just 1 over 5 times an antiderivative for this function. Well, we just saw that an antiderivative for this function is going to be sine raised to the 5th of x. And how do we know that? Well, you could take its derivative and you can find that what you get is you get this thing. So one of the nice things about computing antiderivatives is you can always check your work. And that's a good habit to get into, is always checking your work when you're working these things out. When you compute an antiderivative, check that it is actually an antiderivative. Check that when you get to the end, you get back your original function. Now, what we're going to get here is, remember, it says this is an indefinite integral, so we have to do a plus c. Now I'm going to distribute that 1/5 and have sine to the 5th x divided by 5 plus c over 5. But if I have c and it's a constant and I divide by 5, I just have a new constant. So what I'm going to do is I'm going to write the answer to this as sine 5x over 5 plus c. And this is where working with the c is a little squishy, because why am I not writing c divided by 5? Well, it's just a different constant. If I want to choose the right constant, then I can always choose maybe 5 times c, and I can get back to that, and that's okay. This represents all possibilities of that c. And so if I'm representing all possibilities of that c, it doesn't matter if I write c divided by 5 or c. Okay, so this is your answer. And again, how would I make sure that this is correct? Take the derivative of this. You're going to get back to that. All right, so here is example 4, and we're going to compute the derivative of this integral. Now, what you want to do is you want to think, well, what is this integral here? Well, if I have something like f of x equal 3 raised to the x of 1 plus t cubed, all under the square root dt, that gives me a nice function. We talked about how to interpret that. We talked about how to define that. And it's actually defined for all positive x, as long as actually for all x that go from -1 and on. Now, if I compose this function with e to the x, and I call this some function g of x, then what we end up getting is you replace any of the values of x and f with e to the x. So the only place I see x is up here, so you get e to the x. All right, so you can think of this thing here as the composition of two functions. You're composing this one here, this integral function, with e to the x. And I want to take the derivative. Well, don't try to take the antiderivative of this thing. Don't try to find an antiderivative for big F, because you're not going to do that. You actually can't. Not in terms of the functions that we know for this class. It takes a lot more machinery. I don't know what it is. I would have to look up how to work through something like that, and it would give me a very crazy answer. But we don't need that, because we know that if I take the derivative of big F by the fundamental theorem of calculus part 1, what we should get is we should get the function inside the integral. And one thing to notice is it actually doesn't matter where you start. Remember, the starting point just affects that constant. And if we take the derivative of this, we're always going to get the square root of 1 plus x cubed. And so then, if I take the derivative of g of x, well, that's just going to be the derivative of f of x with the inside function in it times the derivative of the inside function. This is just the chain rule. And so what this is going to be is it's just going to be square root 1 plus e to the x cubed times derivative of e to the x, e to the x. And so what you're going to get is just e to the x times square root 1 plus e to the 3x. And that'll be your answer there. Okay, so again, this is a function of x. And so what we have to do is we have to take the derivative of the inside function or sorry, the outside function, which the outside function is going to be the integral. Take the derivative of that with respect to, or with the inside function in it, times the derivative of the inside function. And this thing comes from the fundamental theorem of calculus, part 1. And then what we're going to have is, again, just e to the x times square root 1 plus e to the 3x. So that's the answer to that. And notice I didn't have to find antiderivatives at all. That's good because antiderivatives of this are impossible. So here's the last example, I guess, of the class. Unless you ask me more questions, we can talk about it on the discussion board. But example 5, if you're given an antiderivative for a function f, and in this case we're calling it capital F, and we know that when you plug in some value, 0 of capital F, you get out 4, then what we want to do is we want to find this specific function. And what we mean by find it, we want to find it in given information here. So we want to compute it in terms of the information that we're given. So what we can do is we can write it as, well, I can pull out a 2, and I have 0 to x of ft dt. And now, the fundamental theorem of calculus, part 2, says this is just going to be equal to 2 times, pick your favorite antiderivative. In this case, my favorite is the one that the problem starts with, and evaluate it from 0 to x. And I guess I should use a t here, because this is the variable t, and I don't want to get that confused with that x. Okay? So now this is 2 times, I plug in x, and I subtract what I get when I plug in 0. Well, I'm given some information. I'm given f of 0 is equal to 4, and so this is 2 f of x minus 4. And now I just distribute the 2. And so my answer in the end is 2 times big F minus 8. And that is what this function is equal to. It's equal to 2 times whatever big F is minus 8. So one thing to keep in mind here is this is not an indefinite integral. It's one of those kind of in-betweens. It's not a definite integral. It's not an indefinite integral. In this case, we're reading x as a variable, and we want to know what this function looks like in terms of the given stuff, what the specific function looks like. So maybe, for example, this is some crazy trig function, and we know that if we plug in 0, or maybe some combination of trig functions, maybe it's 4 times cosine, that satisfies that. Well, if it's 4 times cosine, and then this is whatever the derivative of 4 times cosine is, then I would be able to tell what this integral is in terms of this. You know. Anyway, so that's the idea, and just keep in mind those distinctions between those 3 notational things. All right. Again, if you have questions, feel free to hit me up on the discussion board. I'll try to follow this up with a proof of the fundamental theorem of calculus, but it's been a pleasure making these videos, and yeah.